Welcome to this review of Chapter 5 and 6. Let's begin. The first question asks us to identify each variable as either qualitative/categorical, quantitative discrete, or quantitative continuous. So before I proceed, I'm going to remind myself that qualitative or categorical data is acting as a label. That means it's not counting anything, it's not measuring anything, it's just labeling it. Quantitative discrete counts things. And lastly, quantitative continuous is a measure. So let's begin. The name of a flower, is that a count, a label, or a measure? Well, it's clearly a label, right? It's labeling something. The number of seeds in a packet. Well, can you have half a seed? Well, probably, but it's not going to grow, right? So we need a whole number of seeds, so that would be counting. Then we have minimum hours of sunlight each plant needs. So hours is a measurement of time. So since we are measuring time, we are going to be working with quantitative continuous data. How about the color of the flower? Well, that's clearly a label, right? So it's qualitative or categorical. The SKU number or the barcode number on each flower seed packet. Again, that would be a label. The ounces of water each plant needs per week. Well, ounces is a measurement of weight, or fluid ounces is actually a measure of volume. So either way, it is a measurement. So remember, if you think about ounces, you could have like part of an ounce, you could have 3.5 ounces. There isn't any limit to how far down you can break either volume or weight. All right, minimum temperature needed outside. So temperature, if we are looking at temperature, it's a measurement. Remember, we measure temperature, we don't count it. And lastly, the maximum height of the plant. Again, height would be a measure. Okay, so that is the first 8 questions. Next, we're given a pie chart and shown the grade distribution. And the question says if you have 250 people were represented in this pie chart, then how many of these earned a C? Well, we don't know how many people earned a C, but we do know that 31% of the total number of students earned a C. So we're literally asking, we're saying, what is 31% of 250? And this is actually a skill that you learn back in developmental math, okay? So what is, that's x equals 31%, we rewrite that as a decimal, 0.31, of means multiplication, and then we have 250. So you can type into your calculator 0.31 times 250, and when you type that in, we get 77.5. However, the question says round to the nearest student, right? Because you can't have half a student. So 5 and above, give it a shove. So we were going to round this up to about 78 students. Okay, so about 78 students earned a C in this lecture course. All right, number 10, we're asked to create a stem and leaf plot. So remember, the way stem and leaf plots work is that we literally cut each number in between different place values. So in this case, because almost all of these numbers are 2 digits, we're going to cut between the ones place and the tens place. And in the case of 100, what should we do? Well, we still have to cut between the ones place and the tens place. So you don't have to do this, but you might find it useful to put these numbers in order from smallest to largest. So let me take a minute and do that. Okay, so as you can see, I've put these numbers in order from least to greatest, and one of the reasons I want to do that is because I need to know what stems I need. So as you can see, my smallest stem is a 70, and my highest stem is a 10. And so remember, the rule with stems is that we can't leave any out, even if we don't have any leaves growing on that stem. So we have to have a 7, an 8, a 9, and a 10. Okay, so to represent 72 and 76, we put a 2 here, and then we put a 6 here. And then even though that kind of looks like 726, we don't actually usually put commas in between those 2 digits, the 2 and the 6. Okay, then we have an 80, and we have 3 84s, then we have an 89. So we're done with our 8s. Again, there's 5 numbers in the 80s. Okay, then we have a 90 and a 96, so we put a 0 and a 6 here, and then lastly we have the 100. Okay, so that is our stem and leaf plot. So in number 11, we're asked to use this to create a frequency table with a class width of 10. So to me, the natural thing is to start with 70. So my first class is going to be 70 to 79, 80 to 89, 90 to 99, and then I'm going to go 100 to 109. Now, according to these scores, it doesn't look like you can actually have a value above 100, but, we're still going to use that as a class. Okay? So let's take a minute and just remember, it says a class width of 10, right? And you might be thinking at this point, well, wait a minute, 70 to 79, doesn't that have a class width of 9, not 10? Well, remember, how do we find the class width? We don't take the upper class limit and the lower class limit and subtract them. Instead, what we do is we look at the consecutive lower class limits. So, for example, we could take 80 minus 70 and subtract them, and that is our class width. So if you're worried, oh my gosh, her class width is 9 and not 10, that is not true. This class width is, in fact, 10. Okay? So we can, again, look at our stem and leaf plot. How many leaves, right? How many numbers do we have that begin with a 70? Well, we have 2. So we're going to put a 2 here. How many do we have in the 80s? We have 1, 2, 3, 4, 5. So we'll put a 5 here. We have 2 in the 90s, and we have 100. Okay, so on this next page, we're asked to use the frequency table to create a histogram of the data, again, using the graph that we were given. It says use a bin or class size of 10, well, we already have that, and to make sure to follow all the rules regarding histograms, label your X and Y axes, and write out a title for the graph. So in order to follow these directions, I sort of need to remember, well, what are these values? So if we go back here, right, and read number 10, what are these values? Well, they're about scores on an English test. So my title is just going to be English test scores, okay? And it's kind of boring, but usually my x-axis label and my title are pretty much the same. Okay, so I've labeled my x-axis, I've titled my graph. What should go over here? Well, the title that goes over there is exactly what goes here, which is the frequency. So we can put frequency right here. Okay, so now we have to start drawing our bars. And you can see I've taken a little snapshot of my frequency table just for ease of use, right? So the first class is 70 to 79. Now it reminds us to use all the rules regarding histograms. So remember the rules with histograms, the bars have to touch unless there's a gap in your data. So even though it says 70 to 79, this bar is actually going to go from 70 all the way to 80. Okay, so I'm going to draw a line here, a line here, and a line here, okay, and then just shade it to make it more visible. Okay, the next bar, 80 to 89, it goes all the way up to 5, so I'm going to draw a line here. Okay, and again, that bar goes all the way to 90. It goes all the way to the next class or bin. Okay, and then the next one, of course, is 2, and it looks like this. And then the last one is 1. Okay, and then we're done. That's it. So number 13, this time we have a bar graph. We're working with categorical or qualitative data. And it shows the different kinds of nuts that are preferred by different students. Okay, and the first part of the question says how many people were surveyed. Well, how can we figure that out? Well, what we need to do is we need to look at the height of the bar. So this is 5, this is 8, this is 3, and this is 10. So to get the total number of people surveyed, all we have to do is add those 4 values. So when we add those up, we get 26. So 26 people are represented in the survey. Then it says what percent of people like almonds. Well, we know that the number of people who like almonds is 5. To find the percent, we just do 5 out of 26, okay? And we're going to type that into our calculators. When we do that, we get 0.1923076 okay? Then, to convert it to a percent, we need to multiply by 100%. That becomes 19.230769 blah, blah, blah percent. Okay? And then we need to round it. Unfortunately, these directions don't clarify. So I will try to go back when I edit this. I'll make sure that the directions say what to do. So I'm going to change them so that it says to round to 1 decimal place. So that would be 19.2%. If it just said round to the nearest percent, that would just be 19%. If it said round to 2 decimal places, we would do 19.23%. Okay? So again, you're going to need to round. Okay, then it says how many people prefer peanuts. So let's look at the peanuts bar, right? It looks like there's 10 people. Okay, this time we're not asked for a percent, we're just asked for a count, so that is 10. Okay, then it says what is the relative frequency of people who prefer walnuts? So it looks like there are 3 people who prefer walnuts out of a total of 26. Okay, and remember you can express your relative frequency as a fraction, a decimal, or percent. This one does not specify, so let's just for fun do all 3. So we've already done the fraction. So to get the percent, or the decimal rather, we would just do 3 divided by 26, and that gives us about 0.12 in our calculator, which is about 12%. Okay, so again, that would be your relative frequency. If it doesn't specify, you can use any of those to represent the answer. All right, so now we're back with the frequency table, and as you can see, we have quantitative data. So this table shows the amount of time it takes students to complete exam, and again, the time is in minutes. So the first question says how many students were surveyed. So remember, to get that, we need to add all of these numbers together. So when we do that, we find out that 20 total people were surveyed. Then it says what is the class width. Again, remember, what we do not do is we do not go 9 minus 0 or 10 minus 19, right? We don't take the upper and lower class limits and subtract them. Instead, we look at consecutive lower class limits, so 10 minus 0, 20 minus 10, 30 minus 20, 40 minus 30, 50 minus 40, right? All of those are 10. We could also go 19 minus 9, 29 minus 19, 39 minus 29, 49 minus 39, or 59 minus 49. Again, all of those give us 10. So the class width is 10, not 9. So be careful with that. What are the lower class limits? Well, the lower class limits are all these numbers over here. So there is 0, 10, 20, 30, 40, 50. Those are the lower class limits. What are the upper class limits? Well, the upper class limits, right, are the upper limits in each class. So 9, 19, 29, 39, 49, 59. Those are the upper class limits. Okay, and then last but not least, this asks us what is the relative frequency of students who took between 50 and 59 minutes to complete the exam. So we're just looking at the specific row of data. So the frequency is 4. So remember, to find the relative frequency, we just divide by 20. So if you type that into a calculator, you get actually exactly 0.2 or 20%. Okay, and it says express your answer as a fraction, a decimal, and a percent. So here's my fraction, here's my decimal, here's my percent. All right, the next problem gives you 4 different graphs, and we first have to go through and identify each one of these as unimodal, bimodal, multimodal, or uniform. So let's take a minute and do that. So remember, I taught you in class either the roller coaster test or the blanket fort test. So the roller coaster test says if I build a roller coaster over this graph, how many peaks would it have? So this looks like it has 2 peaks. Blanket fort is the same thing, right? If I threw a blanket over this, right, how many poles does it look like that are sticking up, right? How many people are under the blanket? So this would be 1, right? This would be 1, and this would be 1. So if we have 2 peaks, right, then we call this bimodal. And any graph with 1 peak, remember, we call unimodal. So it doesn't look like I gave you a uniform graph here. Remember, the uniform graph kind of looks like just a boring old rectangle. Okay? So those are the number of modes for each of our graphs. So now let's keep reading. What else does the question want us to say? Well, another thing that the question wants us to answer, it says identify each graph as symmetric, skewed left, or skewed right. So let's go ahead and do that. Well, this first graph here looks like it kind of has a left tail. So remember, when you have a left tail, we say that it is skewed to the left. Okay, this guy kind of looks like it has a right tail. So when there is a right tail, then it looks like it is skewed right. Okay, this next one is pretty symmetrical, right? It's not perfectly symmetrical, but it's close. Again, remember, if you folded it across itself with it on a dotted line, it would kind of match up. Okay, so it's roughly symmetrical. Again, we're not going for perfection here. We're just doing an approximation. Okay. All right, and then last but not least, this guy right here has a big old long left tail, so it was heavily skewed left. Okay, so to sum up here, the first graph is bimodal and it's skewed left. Remember the stuff that's in orange here, right? The number of modes and the way the graph is skewed. These are independent pieces of information. Okay, so bimodal, skewed left. The second graph is unimodal and skewed right. The third graph is unimodal and symmetrical. And the last graph is unimodal and skewed left. All right, here we have a set of 10 data points. It says Josh took 10 quizzes in his English literature class, and the grades are shown below. So it asks us to find the mean, median, range, and 5-number summary. So let's just start by calculating the mean, the median, and the range. So remember, the way we find the mean is that we have to add all 10 digits together. So we have 5 plus 1 plus 6 plus 8 plus 5 plus 2 plus 8 plus 9 plus 10 plus 0. Then, since we have 10 scores, we divide by 10, and that's going to be our mean. So when we add these up, we get 54, and then we divide by 10, so we get 5.4. So the mean of this set of data is 5.4. So now we need to find the median, which is the middle number. So remember, you might be tempted to just go something like this and find the middle number like this. But what is the problem with doing something like that right now? Well, the problem is that these numbers are not in any kind of order. So finding the middle of those numbers, as it is right now, is not a meaningful or helpful process. To find the middle number, the median, what we really need to do is put them in order from smallest to largest. So let's do that. So it looks to me like the smallest number is 0. Then we have 1. Then we have 2. Notice I'm crossing them off as I go so I don't forget any or count something twice. Then I have a 5, another 5. Then I have a 6. I have 2 8s. Oops, let's not put them so close together. Then I have a 9 and a 10. Okay? So, how do we find the median? Again, we find the middle number. So we can just go like this. Okay, and notice that there are 2 numbers in the middle. So you can find the actual median in one of 2 ways. You can find the arithmetic mean of these 2 numbers, which is 5.5. Or you can ask yourself, hey, what's halfway between 5 and 6? And either way, the answer is 5.5. Okay, so the median of this set of data is 5.5. Okay, so remember, the formula for range is simply that we take the largest number and then we subtract off the smallest number. So in this problem, the max is 10 and the min is 0, so the range is 10. So now we need to do a 5-number summary. So again, with the 5-number summary, the first thing we have to do is put them in order from least to greatest. Now, if I were doing this on my test, I probably would just do this, excuse me, one time. I probably wouldn't do it twice. But, you know, since I'm starting over on a new blank sheet of paper, then I'm just going to start over real quick. Okay, then we have 8, 8, 9, 10. Another thing I do, just sort of like a sanity check, is I always count them to make sure I really got 10 numbers. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks good. It looks like I got actually 10 numbers. Didn't forget any, didn't accidentally write 11 numbers by writing one twice. So that's good. Okay, so remember, we've already found the median, right? We've already found the middle number. Okay, and the middle number, as you can see here, was 5.5. Okay, so remember the 5-number summary, and this is something you need to know for a test. It's not going to be given to you. It consists of the minimum value and the maximum value. Then it consists of the median, but when we do a 5-number summary, we don't call it the median, we call it Q2. And then we have Q1 and Q3. Okay, and again, Q2 is the same as the median. Okay, so we already found our Q2, right? We've already found our median, so we don't really need to work for that. We can just say that this is 5.5. Okay, the minimum, of course, is 0, so we can put that there. And the maximum is, of course, 10, right? So that's pretty easy. So really the only work left to do is to find Q1. So notice I've already cut this data set into 2 equal-sized parts. So then I just find the middle number of the bottom half, and that's going to be Q1. And then I just find the middle number of the top half, and that's going to be Q3. So that's it. Okay, so for 17 and 18, we're using this histogram. And not only are we given this graph, but notice we're also given the mean and the median. And we're going to need both of these pieces of information in order to answer number 17. So number 17 asks us, is the graph skewed left, skewed right, or symmetrical? Right? And again, to me, I don't know how you guys feel looking at this graph. It's a little bit hard to tell just from looking at this graph. Honestly, it looks a little bit close to symmetrical to me. So then we have to turn to this information, and we have to remember, well, what do we know about the skewness of the graph as it relates to the mean and the median? Okay, well, what you need to remember is that the mean, this is how I remember it, follows the skew. So what the heck does that mean? Well, I'll tell you, right? So if a graph is skewed left, right, then that means that the mean is to the left of the median, or less than the median. If the graph is skewed right, then the mean, again, follows the skew. That means the mean is to the right of the median. I should probably write these together the same way. I'm going to confuse you guys, right? So if the mean is to the right of the median, that means the mean is greater than the median on a number line. Okay? So let's look at this. Is the mean greater than or less than the median? Well, I think we can all agree that 22.37 is larger than 17.5. Not by a lot, but by some, right? By about 5. Okay, so if the mean is greater than the median, what case do we have? Well, we probably have a case where we are having a graph that's skewed right. Okay, and now that you know that it's skewed right, I guess you can kind of go back and look overall, and it does seem like it has a little bit of a right tail. But honestly, I would be very nervous making that assessment if I didn't have the additional information of the mean and the median. Okay, so I'm going to say that it is skewed right. Okay, and I'm going to explain myself. The reason it's skewed right is because, right, the mean is greater than the median. Okay, and notice in the hint it says one of these sources may be more useful than the other. And again, to me, the mean and the median is a lot more useful than just the graph. Okay, then last but not least, we're asked to describe the graph as unimodal, bimodal, multimodal, or uniform. Okay, so as you can see, I've already sort of done the blanket test or the roller coaster test, whatever you want to call it. There are 2 lumps under my blanket, or there are 2 hills on my roller coaster. So remember, that means it's bimodal. Okay, how would you justify your answer for that? I would simply say there are 2 peaks. Okay, and remember the fancy statistical word for peaks is modes. Okay, so that's it. It's as simple as that, not complicated at all. Okay, so 19 and 20 are basically the same problem. I just gave you slightly different information. And the reason I put 2 on here on the practice is not because they're going to have 2 on the exam, but I just wanted to give you extra practice in case this is confusing for you. Okay, so hopefully you've already read this if you're watching this video, but the idea behind both number 19 and number 20 is the idea of z-scores, or standardized scores. So remember that z-score, the formula is that you take your specific value, which I'll call x, and you ask yourself, well, how far is this value from the mean? And how does that compare with the average value from the mean? So you take your specific value, so you subtract off your mean, and you divide by the standard deviation. Okay, so in this problem, we have 2 populations. So I know there's a lot of issues about not being, not just male and female, and people are identifying as other things, but biologically, biological male humans are normally distributed. Biological female humans are normally distributed. If you try to clump them all into one population, they are not normally distributed anymore. So that's why we're treating them as 2 different populations in this. Okay, so again, biologically male. Okay, so John Corbett, he's a famous actor. He was on the movies, the show, also a movie, I guess, Sex and the City. He played opposite Sarah Jessica Parker. So he's a pretty tall dude. He's 6'5" tall. All right, so we're gonna just use the inch measurement because otherwise our work gets really weird. So we're just gonna say that his specific height is 77 inches. Okay, but what is the average male height? It's not near that high. It's only 68.6 inches. okay, which is about 5 foot 8.6 inches. Okay, and then the male standard deviation in height is 2.8 inches. Okay, so for John Corbett, right, so this is for all men, and this is specific to, I'm going to call him JC, John Corbett, okay? So to calculate John's z-score, in other words, to count the number of standard deviations that he is above or below the mean, we take his specific height, which is 77, we subtract off 68.6, and then we divide by 2.8. Okay, so just a note here, if you are doing this on a calculator and you're getting it wrong, it's probably because the way you're typing it in. So let me just tell you, if you type into your calculator 78 minus 68.6 divided by 2.8, that ain't gonna do it. No, you can't do that. Okay, the way to type it into your calculator, you can do it one of two ways. Okay, one way to do it is you can type in 77 minus 68.6 and then press enter. Okay, so if I did that and then I press enter in my calculator is going to give me 8.4. Okay, so then what I would have to do is then I could take 8.4 and divide by 2.8, and then in my calculator that's going to give me 3. Okay, so his standard deviation is 3. So that is one way to enter it into your calculator. If you're like me and you're like, yo, I ain't got time for that, I'm going to do it all at once, that's fine. The way to do that is to use those parentheses. So if you want to type it in one row, you'd have to type in 77 minus 68.6, then you can close your parentheses, then you can hit divide, then you type in 2.8, and when you press enter there, then you should get a 3. Okay, so that is John Corbett's z-score. Dude is tall. He is 3 standard deviations above the mean, which is crazy. Okay, but Lisa Leslie, I don't know if you've heard of her. She's a former professional basketball player, which kind of makes sense, right? Probably took one look at her and be like, we have a job for you. So we take her height, which is 77, right? But now, right, she's a member of a different population. So again, remember, biologically, we have to separate them if we want them to be normally distributed. So the average female human is only 64.5 inches tall, right? That's a little bit smaller than the average male. Okay, so let me write it out the way I did with the female. With the male. So I'll write. Let me erase this here. All right, female. Okay, so her specific height again is 77 inches. Okay, so if we compare these, they're the same, right? But the average female is only 64.5 inches, right? So if we compare these two numbers, they are not the same. Okay, and then the standard deviation among women's heights is 6.5 inches. Okay, so if we want to find her z-score, remember z-score is the number of standard deviations above or below average that something is. Okay, then we're going to, again, take her height, 77 inches, subtract off the average, which is 64.5 inches, and then divide by 2.5. So again, if you want to put this in your calculator, that's great. Make sure you either put in parentheses or do it in 2 steps like I showed you. Okay, so when you subtract 77 minus 64.5, we get 12.5. Divide that by 2.5, and we get a whopping z-score of 5. So let's reread the question again. It asks us, which celebrity is taller relative to members of their own population? Okay, so again, if we were to just compare their heights, right, if they stood side by side, you'd look at them and be like, they are the same height. So clearly the question is not who is taller overall. That is not what we're asking because they're the same height. It's a stupid question. All right, if I just said who's taller, that's a silly question. Okay, so here's what we need to say. We need to say both John Corbett and Lisa Leslie are much taller than average, right? They're both 77 inches tall. Okay, however, as Lisa Leslie's height is 5 standard deviations above the mean, her height is more extraordinary relative to members of her population, which is biological females, than is John Corbett, whose height is only 3 standard deviations above the mean relative to members of his population, which is biological males. So number 20 is, again, very similar. The idea is that we're going to find the z-score for two different test scores and compare them. So John took an exam in English and an exam in math. So he scored a 70 on the math exam and a 78 on the English exam. So let's write this down. So we have a math exam and we have an English exam. So remember, the z-score, right, is the specific value minus the mean divided by the standard deviation. So we need the specific value in both cases. So his specific value in math is that he earned a 70. In English, his specific value is that he earned a 78. Okay? What was the average math score? Well, the average math score was 75 with a standard deviation of 5. Okay? What was the average English score? Well, the average English score was 85 with a standard deviation of 5. Okay? So then it says, on which exam did he score better relative to others who took the same exam? So as a student who's probably taken more than one exam in your life, you know that not all exams are created equal, right? Some are very difficult, some are pretty easy, right? So it just all depends. So let's calculate the z-score for both exams. So again, we have the specific value minus the mean divided by the standard deviation. So that's going to give us 70 minus 75 divided by 5. So that's going to give us negative 5 over 5, which is negative 1. Okay, so if we were to interpret that right now, that means that he scored one standard deviation below average on his math exam. Again, this means that he scored one standard deviation below average. So let's come over to his English exam. So again, now his z-score, his specific value is 78. So that's compared to a class average of 85 and a standard deviation of 5. So 78 minus 85, well, that's negative 7 over 5. So that gives us a z-score of negative 1.4. Okay, so he scored 1.4 standard deviations below average. Okay, so then the question is, and this one's a little bit trickier, it says, which exam did he score better? So think about exam scores, right? Is it desirable to score above average or below average, right? Well, the higher your exam score, the better you did. So if we think about it maybe like with a scale, right? So here's average, right? 0. A z-score of 0 means you're exactly average. So here's one standard deviation above the mean, two standard deviations above the mean. Okay, then we have negative 1, so one standard deviation below average, right? Negative 2. Okay, so let's mark this, right? So on his math, right, here's math. Let's make math blue. Okay, so here's his math exam. Okay, he scored one standard deviation below average. And then I'm going to make English red. Okay, so for his English class, he got 1.4 standard deviations below average. So if we look at this picture, right, this blue here is how far below average he did in math. Okay, this red arrow shows you how far below average he did in English. So where was he farther below average? Well, wasn't he farther below average on his English exam, right? So farther below average means he did worse, right? The farther left you are, the worse you did, right? The closer to average or the farther above average you are, the better you did. Okay, so he actually did better on his math test. Okay, now could you tell that just by comparing the numbers? Absolutely not. Right? Because objectively, if we just assume, well, these are all percents, right? So they're all out of 100, right? A 78% is higher than a 70. Okay? But again, they're not the same exams. They're completely different exams and completely different subjects. So we're not comparing the 70 to the 78. What we're doing is comparing the 70 to the rest of the class, right? Who took that same exam. And then we're comparing the 78 and we're comparing it to the rest of the class who took that English exam. So let's summarize our answer. We can say that John has a z-score of negative 1 on his math test, and that means he scored one standard deviation below average on his math test. He has a z-score of negative 1.4 on his English test, which means he scored 1.4 standard deviations below average. So that means that he performed better on his math test than on his English test. His English score was farther below average, meaning he did worse relative to other classmates who took the same exam. So the last question on this review asks us to calculate the standard deviation. Notice, luckily, on this problem, we are given the formula for standard deviation. So all we have to do is crunch the numbers. Okay, so the first column, I'm going to just enter my values. So my data, we have 4 days of the week where I recorded the number of cookies that I ate. So maybe I have 1, 2, 5, and 0. So remember, the first thing that I have to do is I have to calculate my population mean, which is 1 plus 2 plus 5 plus 0, divided by 4. So that's going to be 8 over 4, which is 2. So then the next thing I have to do is I have to take my specific value and subtract off my mean. Okay, so let's go ahead and do that. So I'm going to have 1 minus 2, 2 minus 2, 5 minus 2, and 0 minus 2. So that means I get negative 1, 0, 3, negative 2. So then I take all of those numbers and I square them. So I'm going to have negative 1 quantity squared, 0 squared, 3 squared, and negative 2 quantity squared. Okay, so I can just put this in my last column here. Negative 1 squared is just 1, so I have 1, 0, 9, and 4. And then I can add all of those together, and I get 14. Okay, so we're almost done. So what we have to remember is that this 14 is equal to, this isn't the right thing. The summation should only be right here. So it's equal to this thing. It's the sum of x minus mu squared. So we have the square root of 14 divided by n. Well, what is n? Well, n is our population size. So there's 1, 2, 3, 4 data points, right? 1, 2, 3, 4. So our n is 4. So remember, you have to put this into your calculator carefully. You can either do it all at once, square root of 14 over 4, make sure you use your parentheses correctly, or you can type in 14 over 4 and then do the square root of that. Either way, you should get about 1.87 for your standard deviation.